All right, we're in section 16.2 and we're about to do example 5. So 16.2 is line integrals, and so far we've been doing line integrals that have a ds at the end. So now we're going to see ones that have a dx or a dy at the end, or as it turns out, in the middle, which is really weird. But anyway, so take a look out for that ds situation is what we had before. The way we're going to do a conversion here, we're actually still going to convert to t when we have a dx or a dy, which again, and if you see in this example 5, they can actually be in the same integral. Again, that's kind of strange. It looks like a typo. Our goal is to write that in respect to t, and then we're going to do that line integral just with respect to t, so it'll be very similar to what we did with the integral with respect to s, converting that to t. So one little thing that's different is what we have here is, instead of having that root with the derivative squared for each component, now we have just the derivative with respect to that variable associated with the corresponding x or y with the dx, or the d part. Alright, so that makes sense in the context of u sub, that if you let you have your dx here and you're trying to write that in terms of t, then your dx over dt can be represented as x prime of t, and that dx then is x prime of t dt, with solving for that differential dx. So you just do your stuff there, and then you do that integral with respect to t as we were doing with ds. Okay, so here we have again this integral that looks a little strange. It's a line integral of over c, and we have a dx and a dy in there, and so you're going to convert each of those, kind of thinking of it component wise, to t, and then we're going to have an integral that's kind of more harmonious, and we can actually evaluate it with respect to just the one variable t. So with c, we got to represent that, and we're told that it's the line segment joining -5, -3 to 0, 2. Alright, so we already did this with an example, and we're going to do the same thing, where let one of the points be your p naught, or each component, or not component, each coordinate be x naught, y naught, and then the other one x sub 1, x or y sub 1. And then this vector equation of a line, the parametric form of that, has that 1 minus t, and where that comes from is something we've discussed, but it's specifically for t going between 0 and 1 by design. And then those will be our limits of integration. So we use that form and we plug in the things we need. So with this x form, again, this is only in 2D, so we don't use the z. We plug in our x naught and our x1, do a bit of simplification, we get -5 plus 5t for x. Similarly for y. And then we have our parametric equations. The other thing we need to do, we need to convert, again, those dx and dy by using the derivative of x with respect to t dt for this dx, and then y prime of t dt for the next one, and then they're both in terms of dt. So finding those is pretty easy. That both end up being derivatives of 5. So we put all this stuff in here, and again, these limits of integration by design are 0 to 1. Now again, this looks a little strange to have two dt's, but basically you can kind of think of factoring that out and putting it all together. And now we have a more normal looking integral with respect to t. So go ahead and simplify that. Expand the square, combine like terms, and then we do our integral. It's not too bad. So we get an answer of negative 5, 6. So that's fine. Just a little add-on here. What if we did this example with the order of our parametric equations switched? So I just kind of did that work pretty quickly here, and just kind of to show you here that that order does matter. We get different parametric equations. And it's like our t equals 0 starting at a different place, going to t equals 1 with the opposite point and ending there. So what do we get? We get 5, 6. So notice that we just got the opposite sign. And before, with ds, you had to kind of take it for granted, but I told you that the order didn't matter and you got the same answer. That's because when you do that integral with ds, that the delta s is always positive in the way that you're doing that integral, and it doesn't matter on the order or direction on that parametric curve. But when we set up these integrals with respect to x or y, then x or y can be negative, and then the direction does matter with regards to parametric equation. But it matters in a way that you just get an opposite answer. So that's something that's good to note, because theoretically, if there's an easier way to do it, you could just do it that way, and note that the sign could be different than the way that maybe was intended or implied by the problem. Okay, one last example, one last thing in this section, but the next section continues on with line integrals. So this is it for line integrals for now in this section. And that's line integrals of vector fields, or in a vector field would probably be a better way to state that. I'm actually going to modify that. So we can, kind of the type example here is work done along a curve C in a variable force field, which we're going to define as big F. So we can do this with a line integral that's defined in this way down here. Also, there's other contexts for which we'd want to do a line integral in some sort of field or vector field. And so this definition in your book is pretty generic, but we can pretty much take it for work. The problems in your book are of the generic form. For example, example 6 here, it says evaluate the line integral of the vector f dot dr, which is weird, but we'll get there in a minute, where big F, and then we are given that as in vector, and C is given by the vector r, which is also, of course, a vector. We're given the t varying between 0 and pi. Alright, so let's go back to this definition 13. And notice that this is kind of similar looking to our f dot d, and then if we break down the dr with that dot product, that what that can translate to in terms of r, the vector r, is then this r prime of t dt. So we're going to do this integral with respect to t. Really, we're not going to use this last thing, but t there is the unit tangent vector. But again, we're not going to do problems like that. Okay, so some side work here to do. We want to plug into this line integral form. Might be worthwhile just to kind of work on the stuff in here. So find big F of r of t, and we're given big F, we're given r of t. So when you plug in there, you're plugging in terms of t. So when you look at your r, notice that it's component wise, and that each component is going to match up with plugging in for the x and the y here. So for example, x is equal to cosine t, so that's how I decide to plug that in there. Okay, so that's what the f of r of t is about. Then you're supposed to dot that with r prime of t, which is a vector. So go ahead at some point and find that derivative. If you need a refresher on that, you just go ahead and take the derivative component by component. So that's what we get there. And then the dot product is fairly easy. Reminder on that, you just multiply component by component and add it up. So we get some nice simplification going on with the first two terms. We just get 0, and we have that third term to finish things out. Okay, the purpose of that, by the way, I forgot my dt. I did not carry that long. Better do that. Got lost in action there. And so when we put this integral together, we want to start working on the integration. It's from 0 to pi, which was given, and then we just have our result there from the f dot dr. Easy use of let u equal sine t. We do this integral, we get 1/2 u squared, back substitute with u equals sine t, and then plug in, and we get the dissatisfying answer of 0. And that's it on that one. And that's actually it for this section. So we're not done with line integrals, but that'll be continued in the next section.